And now let's prove this theorem 3.2.3. And we're going to prove it for the, the row operations. So we'll go through all three of those and leave the column operations as a similar argument. Okay, so let matrix A have the usual entries, A sub ij. It's an m by m matrix. Let's consider row interchange. When we swap row P and row Q, first we'll make the elementary matrix, E sub PQ, by interchanging the qth row and the pth row and the qth row of the n by n identity matrix. More specifically in terms of symbols, take I sub n, interchange row P, row Q. That gives you elementary matrix E sub PQ, and let its entries be E sub ij. Okay, so a bunch of zeros and n ones. Where are they specifically? Well, mostly they're in the same place they were in the identity matrix, except for row P and row Q. So if we stay away from row P and row Q, let I be an index other than P or Q, then E sub ij is going to be 0, provided I and j are different, and E sub ii is going to be 1. In other words, the non-P and non-Q rows of matrix E sub PQ, they're the same as the rows, corresponding rows of the identity matrix. So 1 along the diagonal and 0s off the diagonal, except for rows P and row Q. So we need to look at row P and row Q and see what we got going on there. For I equals P, looking at row P, we've got E sub Pj equals 0, provided j doesn't equal Q, and E sub PQ equals 1. That's because we ought to see the kind of behavior we'd have in the qth row. In the qth row, we got a 1 in the qth column, like we do here, and 0s everywhere else. So that's exactly this, except we've changed that first index from a Q to a P. So 0s away from this entry in the qth column and a 1 there. Similarly, when we look at I equals Q, now the qth row of this E matrix, we get 0s when we stay away from P, and we get E sub QP equals 1. So what happened in all that stuff was everything's the same as the identity except the pth row and the qth row. In the pth row, we've got E sub PQ equal to 1, and in the qth row, we've got E sub QP equal to 1. So that's the pattern on how these things have swapped around. So let's see what happens when we take matrix B, or take matrix E sub PQ, multiply it by A on the left. Let's call that matrix product matrix B with entries B sub ij. Okay, a lot of stuff is going to look like matrix A because a lot of the pieces of this elementary matrix look like the identity. So we've got B as an m by n matrix. If we look at the non-PQ rows of matrix B, what we're getting, so let J vary here, we're getting B sub ij is a sum from k equals 1 to n, E sub ik, B sub kj. All right, we stayed away from the P and Q, the strange rows. So we're getting 0s except for when k equals I. When k equals I, then this entry is 1. And when k is not I, these little subscripted e's are all 0s. All right, so when k equals I, we'll pick up a thing here. We'll get a B sub ij as predicted. Hey, B sub ij, same as A sub ij. So I've got a typo here, I should have A's here. We're taking the product of the elementary matrix with matrix A, and these should be A's. And we'll get 1 times when k equals I, we'll get A sub ij out as claimed. Sorry about the typo. So we're in good shape when we stay away from P and Q. The ith row of B is the same as the ith row of A. Now let's look at I equals P. And when we do that, I should expect to see some almost misbehavior. This is not going to work out quite the same, but remember when I equals P, we've got a bunch of zeros when I equals P, except for E sub PQ is 1. So same thing, there's got my A correctly here. When we look at the B sub PJ entry, okay, here's how you take the matrix product. I got the P and the J there. Oh, these things, these are all 0 except when K equals Q. E sub PQ is 1 and E sub QP is 1. So we're getting all zeros for these except when K equals Q. When K equals Q, then we'll have an A sub QJ over here, and this gives out A sub QJ because of all the zeros. So we get B sub PJ equals A sub QJ, and that's valid for all appropriate J's. So the Pth row of B equals the Qth row of A. Talking about in the matrix product now, as desired. The Pth row of B is the same as the Qth row of A. Similarly, when we take I equal to Q and we look at the product, you're getting all zeros from this except E sub PQ. Yeah, E sub PQ equals 1. That's on this slide. We'll pick up a 1 there. So when K equals P, we get A sub PJ out, all the other zeros give us nothing. And so we get B sub QJ equals A sub PJ, valid for J over the appropriate range. In other words, the Qth row of B is the same as the Pth row of A. So indeed, in this product, we've effectively taken matrix A and interchanged row P and row Q. Let's do the same thing for scalar multiplication. Okay. Row scaling, as they call it. Let's take row P and multiply it by S. For an elementary row operation, S by definition is non-zero. We could probably have, if you took S to be 0 and you followed the same protocol, forming an elementary matrix, E sub 0 P, I might call it. I think it'll work in that case as well, but we don't count that as an elementary row operation, so it doesn't become part of the conversation. So take row P, multiply it by non-zero scalar S, then we'll form elementary matrix. Let's call it E sub SP, S for that scalar that we're multiplying row P by multiplying the Pth row of the n by n identity matrix by S. So we'll take the identity matrix, multiply row P by S. Okay, the identity matrix is mostly zeros. And that'll produce this matrix E sub SP, let's also call the entries lowercase e sub ij. So E sub ij is 0. If we stay away from the Pth row, whenever I and j are different. Otherwise, when I equals j, we get 1 out along the diagonals. When we look at the Pth row, well, we get zeros out except on the diagonal. And at that diagonal entry, which will occur at E sub pp, we took I equal to p, we'll get s times 1. So there's specifically what we get out for the E values as we did above. Let's go through and take that matrix product, and here's what happens. So in the matrix product, then if we stay away from P, we'll get this kind of behavior. The entries of the elementary matrix times the entries of the A matrix. Okay, bunch of zeros here. We stayed away from the Pth row, so the only time that double subscripted E's are non-zero is when K equals I. So when K equals I, we get a 1, otherwise we get a 0. So over here, when K equals I, we'll get A sub ij. This is the formula for B sub ij. B sub ij, A sub ij, same for all those rows except for the Pth one, as needed. What happens on the Pth row when I equals P? Okay, same kind of thing, except we've got a P in this position. Now we're getting out zeros except when k equals p. And when k equals p, this entry, it ain't 1, it's s. So when k equals p, it's the only time we get a non-zero double subscripted e. It will be s at that time. K equals p will produce then s times a sub pj, s times a sub pj. So b sub pj equals s sub pj for all appropriate values of j. That is, the pth row of matrix B is s times the eighth row of matrix A. And that's what we claimed there. We'll leave row addition as exercise 3.d. Similar manipulations. The elementary matrix changes, only changes in row P. It's only row P that's changed, and it's changed in a specific way involving another row. And you go through and find the entries in terms of the elementary matrix times matrix A and show they are as desired. Column operations, similar manipulations. Multiplication on the right by the elementary matrices there, but same type of arguments. Okay, to the notes. We could find determinants of elementary matrices quite easily. If we've got an elementary matrix that interchanges two rows, why, that'll change the determinant by a negative. We've taken the identity matrix. Identity matrix certainly has a determinant of 1. Determinant of the identity matrix is easy. It's upper triangular, however you like to justify that. So we've taken the determinant here and by row interchanging modified it by a negative. So the determinant of the associated elementary matrix, E sub PQ, would be negative 1 times 1. Row scaling, you pick up a factor of s. So the determinant of the elementary matrix would be s times the determinant of the identity. So the s times 1 is s. And when we did the row arithmetic, well, that doesn't change determinants, row addition. So the determinant of one of these, we'll denote that, as you'll see in the proof, was E sub PSQ. This is a notation I'll use. I guess I didn't do the proof for that part. But we've taken P and added S times Q to it. So I'll use that little notation to represent that. A determinant of that is the same as a determinant of the identity. This type of manipulation doesn't change determinants. That was one of those theorems from the previous section. We know how elementary row operations affect determinants. Elementary column operations will behave similarly, correspondingly. So we can easily find determinants of some elementary matrices. Okay, here is potentially a rather involved result. For n by n matrices A and B, the determinant of the product is the product of the determinants. Well, it ain't hard for us because we've got some background knowledge about determinants of certain kinds of products. Tell you what, let's take a peek at, I need to start from scratch. I should have had it pulled up already. Let's go to the notes from 3.1. I've got everything at fingertip out there posted online. And one of the last results from this extremely lengthy section dealt with a certain kind of partition matrix. Come on, let me slide down. Here we go, this is it. Theorem 3.1G. Okay, we had a matrix partitioned up where we had zeros, the zero matrix of the appropriate size in the upper right, or for that matter in the lower left. And we saw that when we took the determinant of a partitioned matrix of that sort, we get the product of the determinant of these two matrices, I'd like to say along the diagonal. That's misleading, as we commented at the time. But this kind of makes me think of an upper triangular matrix. Sorry, lower triangular matrix for this one, upper triangular for this one. They're not, as explained earlier. But that's one way to remember this little formula, in my opinion. But we know if we've got the zeros up here in a matrix partition like this, the determinant of that matrix is the determinant of this one in the upper left times the determinant of this one in the lower right. We're going to use that in proving this product formula. So it's not going to be quite so bad, but we got a certain body of knowledge behind us now. All right. So we're going to prove the determinant of the product is the product of the determinants. All right. Hey, determinant of A times determinant of B. Theorem 3.1.g says we could write this like that. We could take a matrix, partition the matrix with matrix A in the upper left, matrix B in the lower right, zeros here, didn't really matter what we put here. For some reason, we're putting the negative of the n by n identity. Fine, I can put anything I want there. Theorem 3.1.g said the determinant of that partition matrix would be the determinant of A times determinant of B. So we're not so hands-on, thankfully, in terms of components of a product, right? Going through finding the IJ entry of this thing and then computing determinants and cofactors and all that stuff. So we've kind of buried that by using this. Really, this is the workhorse, I think, is Theorem 3.1.g. Okay, we're going to take this and multiply it by an upper triangular matrix. All right, this really is upper triangular. Along the diagonals, we've got n by n matrix here, n by n matrix here. Notice B is n by n, so there's no holes. That zero matrix must be an n by n matrix of zeros. But what we've got is ones along the diagonal, because these are identity matrices. Below that diagonal, we got zeros in this part. Yeah, you got zeros in this part and this part too, because these two matrices are identity matrices. So this is a partition of an upper triangular matrix. Theorem 3.1.h said you take a matrix, multiply it by an upper or lower triangular matrix, doesn't change the determinants. While it's at our fingertips, that was Theorem H. Yeah, if we had T as an upper or lower triangular matrix, or with ones along the diagonal, and then we get the determinant of matrix A times this upper triangular matrix is the same as the determinant of A. So multiplying A on the left or the right by such a matrix doesn't change determinants. That's what we're doing here, where this is matrix T. It's got ones along the diagonal as we required. It's lower triangular, all zeros below the main diagonal. All right, so the determinant of this thing is the same as the determinant of this thing times that matrix T. T is of the right sort. This matrix is of the right sort. Diagonals on the entry and upper triangular. Okay, we know how to multiply such matrices. Theorem 3.2.2. So one of the things we did in this section said, you multiply partition matrices, you do it the way you do, just product of 2 by 2 matrices. So we get A times the identity plus 0 times 0 here, which is A. A times B plus 0 times I here, so we get AB here. Negative identity times identity plus 0 gives us negative identity here. Second row, second column would give us negative identity times B. That gives negative B plus B times identity plus B. Give us negative B plus B, give us a 0 down here. And that's why we chose the negative signs. But Theorem 3.22 confirms this for that matrix product. All right, now we're going to move some things around. What we're going to do is swap rows I and row n plus I for I equals 1 to n. So we're taking the first row and moving it down to the n plus ith row. What we're doing is taking the first row up here in the A and the AB part and swapping it with the first row in this part. Remember, all these matrices are n by n, so the dimensions are easy to deal with. We're effectively moving the A and AB part down and the negative I sub n 0 part up. So we're really swapping those. We need to do row operations. We can't swap huge blocks at a time. So we have to do it in terms of row operations. So we'll know how determinants are affected. So we're doing how many swaps here? N of those swaps. So we're changing the determinant. If we talk determinants, we're changing that by a factor of -1 to the n, because we know how row swaps affect determinants. So we're doing one at a time row swaps to produce this matrix from this matrix. Okay. Oh, excuse me, we're getting, I should have pointed down here, we're getting this matrix from this matrix out of the swaps. So we're changing this, the matrix we're given, into this matrix here. We've moved the A and the AB down and the negative I sub n and zeros up. How does that affect determinants? Theorem 3.1.c tells us that. Tells us that it affects determinants by a factor of -1 to the n power, however many row swaps you did. So -1 to the n power, determinant of that modified thing, that'd be -1 times, to this we can apply what we had above. That'd be the determinant of this times the determinant of the AB. Hey, the determinant of -I to the n. So if I multiply a matrix by a scalar, the whole matrix by a scalar, then we have effectively multiplied each row by that scalar. There's n rows, so you pick up a -1 factor n times. So we get another -1 to the n out of this times the determinant of I sub n, which is 1. So we get a total of -1 to the 2n, -1 to the n from those row swaps upstairs, this determinant thing, effectively multiplying a row, n rows by the scalar -1, produces another -1 to the n. We get this, fortunately that's even, and we can drop that -1. So what we've got then was that the determinant of A times the determinant of B, that's how we started this. We had it down to this. Then we did this row swap stuff. Okay, that introduced the -1 to the n. We just saw we can write that in terms of this, -1 to the 2n. Why, that's just 1 times the determinant of AB. So we get a determinant of AB on this part. And the determinant of A times the determinant of B is the determinant of AB. As far as proofs of this go, that was pretty slick. Of course, we borrowed a lot of stuff from the past. Properties involving partition matrices, and I doubt you did partition matrices in linear algebra. You may have seen this result, but I would be quite shocked if you actually proved this result in sophomore linear algebra. If you did, it wasn't nearly as clean as this, because here we've got a good body of knowledge on which to base our proof. And back to 3.2. Okay, a little comment. We're going to consider vectors in Rn as column vectors, or if you like, n by 1 matrices. So if we're going to write matrix X, vector X as a column, then to make reasonable writing in terms of the notes, we'll write it as a row vector and then transpose it if we're treating these as column vectors. And nobody much cares until you start trying to take matrix products, and then it matters whether I've got rows or columns, and we usually want columns when we multiply matrices, not exclusively, as we'll see. So if we take n by m matrix A and a vector x from Rn, then Ax is defined. This is column vector, it's n by 1. So if we've taken n by m matrix A and x is from Rm, then we'd have m by 1 matrix here, and the dimensions line up. The second dimension of A is the same as the first dimension of x, so this is defined. And those type products are of particular interest. Let's see, we could transpose the A, taking x from Rn, then the transpose will be, it'd be 1 by n, then we'd have a 1 by n matrix times an n by m matrix. Second dimension here is n, first dimension here is n, they're the same. So that matrix product exists and results in a 1 by m matrix, if you like. It'd be a row vector, arguably. But we can multiply matrices times vectors, and also multiply vectors times matrices, you know, if you really even want to distinguish between vectors and matrices, provided the dimensions line up properly. If we're treating them as column vectors, we'll have to do a transpose to have that product exist when we multiply the vector on the left. Now, as I said, products of the form AX are quite important where the X is a vector. Let's denote the M columns of n by m matrix A as A1 through A sub m. We've done a little bit of that in the past. Previous section, we did some proofs where we labeled columns of a matrix in terms of subscripted vectors. So let this be the columns of matrix A, the column vectors if you like, and consider X a vector in Rm, column vector by convention. If we look at AX, matrix A times vector X, then what you're going to get, as you see in linear algebra, big observation, you're going to get a linear combination of those column vectors. It comes out of the row times column way that you multiply matrices. So AX is a linear combination of the columns of A, inspiring me to think about column spaces. The column space of a matrix is the span of the columns of that matrix treated as vectors. AX, any product of this sort, is a linear combination of those columns. So we've got AX as an element of the column space. Can you tell me what coefficients to use on the columns? Yeah, use the components of that vector, and that'll tell you what you've got in the column space. This means, this gives me kind of a link between column spaces and systems of equations. If you're looking for solutions X to the system of equations, AX equals B, AX equals B, you're probably used to having little arrowheads over the X and the B, but not in here. But you write systems of equations in terms of matrices and vectors like this. Solving that is equivalent to determining whether vector B is in the column space of A, determining whether vector B is a linear combination of the columns of A. Are you going to have a solution to this? Well, yeah, if B is in the column space of A, you will. If B ain't in the column space of A, then you won't. So these solving systems of equations type questions can be translated into questions about column spaces. I bet you if we looked back upstairs and we focused on this, we could probably have some sort of interpretation in terms of row spaces back up here with this transpose and multiplying on the left. Okay, so we'll stop there and pick up next with outer products of matrices and their properties. So we'll get there shortly. Bye-bye.